The first thing we're going to do is take the 1.6 amps and multiply it by what? 0.9. What does that give us? Okay, so this is the manufacturer's overload chart. This is not necessarily the one that you'll have, but your manufacturer comes up and provides this for us. Okay. So right off the bat, so we multiply by 0.9, what do we get? Okay, is it single phase, three phase, how many units are we going to use? So if I was using single phase low voltage, this would be it. Single phase high voltage, this would be it. Three phase high, three phase it would be it. Right? You understand that? Yes or no? So what would we do? So we take 1.6, we multiply it by 0.9. What does that give us? 1.4. I find that in my chart. Where's that in my chart? No, we got two choices. What we're looking for is between, if it comes up to be exactly 1.4, then I would look at the first one, right? You understand? If it comes up to be greater than 1. So if it's between 1.28 and 1.43, I would use a V2.110 for this manufacturer. If it's between 1.44 and 1.62, I would use a V2.40 for mine. So what does ours come up with? So it's greater than 1.44? Okay.
It's 1.44.
Okay.
The highlight.
It is 1.44?
Exactly.
Okay, so we use what? Okay, I understand now. Somebody said 1.4, and that's what I was explaining. 1.44. So let's see if it's going to be okay. First of all, what we'll do is it cannot be greater than 125% of the low current. So what we're going to do is we're going to check it, and we're going to see if it comes up to be greater than 1.62. Then we'll go to the next higher. If it comes up to be less than 125%, we'll use the other. Nancy's trying to comment. So let's say, note that the full load current on the nameplate, service factor of 1 multiplied by 0.9 for the following procedure if use full load current. Find an overload in the current where the full load current falls within the range. Multiply the minimum overload by a trip current of 1.25.
Well, I just did 1.44 times 1.
So what we're going to do is we're going to divide this by what? Sorry. Multiply by 1.25. Then we're going to divide the answer by the full load current. .44, right? And you can do this in your head. If it comes up to be less than 1, then we're going to use what? Take higher. If it comes up to be greater than 1.25, then we use what? Okay, so we'll check this and see if that.
If it's 1 point, okay. Go back to what you said, multiply. Are we multiplying 1.44 times 1.5, then dividing that?
We're multiplying the minimum full load current, and we knew that one because we looked it up, right? So what's the minimum full load trip current? 1.44. Okay. Now we're going to see if this is okay, if it's within the 125%. So your overloads are supposed to be 125% above. So if it comes up to no more than 125%, I'm sorry. So if it comes up to be more than 125%, then we'll move to the next one. If it comes up to be less than 100%, we'll move to the lower next one. Right? You understand that? So what we're going to do is we're going to multiply the 1.44 by 1.25. Then we're gonna divide that by the full load current. What's the full load current? 1.44. What do you come up with? Okay. Comes up to exactly 1.25. So what is that?
What's the 1.25?
1.25 is the maximum that we can, the maximum that we can protect. Okay, so that means, huh?
That's on the load.
No, this is choosing the overlay. This should, the procedure there should be a detective somewhere. I don't know exactly.
1.44 times 1.25 divided by
1.44, right? 1.25.
so now you want to go lower.
Well, yes and no. Yeah. So this overload will be okay. Very seldom you'll find an overload that would not be okay. Every once in a while you do, especially when you get towards the low end and you get towards the high end. What worked out here is that our current fell right on one of the overloads, right? So that was pretty close to it, but if it came up to be like 1.26, then you do lower, because you went over 100%. If it come up to be less than this, then you go to what? This time. Okay. Are you okay with this? Casey, if I gave you the procedure, you go do this, if I gave you all the procedure. Yeah, we'll see. Now you have to understand, this is the overloads for this company, right? Y'all understand that? So what you need to do is you need to get the chart for the overloads you buy the company from. I mean, the company you buy the overloads from, not the. These are, this is in your book too. This is the chart that comes right out of the National Electrical Code. And what this does, if you've lost the faceplate on your motor, but you know the horsepower of the motor, then this gives you some generic figures that you can use to size your overload. Now, if your motor has got a nameplate on there, or legend plate on it, that's what you need to use, right? Y'all understand?
And most manufacturers
Well, the problem is that most motors can be rebuilt. Usually what happens on the induction motor is the rotor very seldom goes out. Sometimes the bearings might go out. And what normally happens is when your stator cord will turn. So they'll come up and they'll take that thing and tear those stator cords out and come back and rewire it. It goes into the shop and, they down them around and stuff. And the nameplate is usually riveted on there. And a lot of times when they rebuild them, they'll paint them. If the nameplate is not embossed like they do a lot of times, it's just painted on there, then they cover up every bit. And then you can't read it anymore. Try to scrape off the paint, you scrape off all that bit. So no, on a new motor, you're exactly right, it's going to be on there. But this guy right here is nothing but a stick. And it's not embossed, it's not metal. So if they came up and rebuilt this and they repainted it, which they probably would, then usually they'll dip it in an acid to try to get rid of all the lacquer when they get the lacquer dip. A lot of your big motors, they'll wind it and then they'll dip it inside lacquer. So what they do is they seal those coils up in there. You get into a real high current motor, and those wires have a lot of magnetic strength. They're constantly trying to push each other apart because current's flowing in the same direction. So this guy creates a magnetic field in the same direction on that one. And that's what you're hearing when you hear transformers and everything. You're hearing those same wires do what? Yeah, they're trying to push apart. I mean, That's what they do. They drop back in, and they get current, they push forward, and that's what you hear winding. So if you ever got into one of those big old transformers on the pole, you see those suckers are dipped in lacquer. So they wire it, and then they dip it down in this paint, and just to do what? Just to seal those windings up real good to keep moisture out of them. But that's not really true, too. They dip them, they put those in oil. Oil is a good insulator, and plus it's a good cooler, too. It prevents moisture from getting into the transformer. We got a video of how those power control transformers are made. This is in the National Electrical Code. I don't know what table it is, but you can look it up. But this is what we would use generically if I knew what. By the way, this is induction motors will never, ever, ever run at the same speed as the field. So what happens is the field is rotating around the outside, and then your rotor, to induce a voltage into the rotor, you got to have a difference in frequencies, right? You understand that? So on a induction motor, the rotor will never run at the same speed as the field. So it always runs slower, and they call that slip. The less horsepower you desire, less slip you have. The more horsepower you have, the more slip you have. So the speed of the motor is rated for what? If you're running at the what? The rated horsepower, at the rated frequency, at the rated voltage.
Plus or minus this.
Anybody know? So what we do is we got a pair of poles. We make one rotation per pair. Okay. But the problem is that our frequencies in cycles per second, and our motors is in revolutions per minute. So to calculate the speed of the field, what we would do is we would take it won't let me draw. I know why it won't let me do it. It loaded up a different version of it. It recovered it. So we make one revolution for one pair. If we had two poles, then we would make one revolution for two pairs, right? Does that make sense? So the more the magnetic poles the motor has, the slower the motor runs. So anybody know the formula for the field speed for a induction motor? Anybody know? So to calculate the speed in cycles per second, we would take the frequency and then we would divide it by the number of poles, magnetic poles. Or some teach the number of frequency by the number of pole pairs. No, our frequency, what's Alabama power? Okay, Alabama power is 60, right? Y'all understand that? But your frequency is rated in cycles per second. Your motor is rated in revolutions per minute. So if I know this, if I take my frequency and divide it by the number of poles, that would be what it would try to run per second. So what would I do to my out by the per minute? Well, I would here because so I'd multiply it times 60. So we got to have at least two poles, right? We got to have a north and south if they're swapping. But we don't say two-pair motor. We don't say a two-pair motor. We don't say a three-pair motor. We call it a two-pole motor, a four-pole motor, right? You understand? So what we do is we take, if we're dealing with the number of poles, then it's times 120. So if I got a two-pole motor, that means a north and a south that keeps swapping, right? Then that would be 120 times the frequency. What frequency did we use over here? 60. Divided by the number of poles. And that should give us the speed of the motor, which is 3,600 RPM. I don't do it in my head. It's just that I know a two-pole motor runs at 36 miles. So these are the field speed. This is not the speed of the motor. The motor is going to run slower because it's got to have slip, right? So that motor right there is running at 1785. So it's a 4-pole motor. So if you put 120 times 60 divided by 4, it'll come up and give you 1,800 RPM. So when you look at your motor, you're not going to see 3,600, you're not going to see 1,800, you're not going to see 1,200, you're not going to see 900. What you're going to do is you're going to see the slip, right? You really need to talk to me. So y'all understand that where the 120 came back? Because so what we're going into is we're going from cycles per second to revolutions per watt per minute. And this is not the speed of the motor, this is the speed of the field.
Why am I getting this?
What do you mean?
I did the 120 times 60 divided by 2. I got 120. You got 7,200 before you do. I got 7,200 divided by 2.
So for 120 times 60, sounds like you're dividing by 4. So you're doing something there. Yeah, so a two-pole motor runs 3,600, right? A 3-pole motor will run at 1,800. A 4-pole motor will run at 1,800. You go in pairs. So we go 2, 4. What would be the next one? 6. Well, this is what they do. So this is one way that they change the speed of a motor. So if you got a ceiling fan in your house, you flip that switch. What do? Changing the number of poles. If you look, it's got 3 wires coming out, and that's all it's doing. It's shifting either more or less poles. This guy right here, this is a 3-speed motor. So what do we do? So this is the start capacitor. The 2 brown wires are the start capacitor. The yellow is the common, and there's your 3 wires. And what are you doing here? You're changing the number of poles. So these have fixed speeds, right? This is a 3-speed motor. If I can carry it all over the place, then what do I got to do? So if I got a motor that I want to control the speed of, I can't change the pole. What do we change? Got to change frequency, but we can't just change the frequency because of something called XFL. We'll look at that later. And then Nancy talked about this. So they call them variable frequency drives, but the name is changing. People understand that you just can't change the frequency. Okay, you got to change the frequency in the motor. So I call them variable speed drives, but everybody over in Germany will call them what? But Nancy maybe put that in our PowerPoints because they wouldn't know what we was talking about. Of course, those guys didn't know that much about motors anyway, did they?
Wasn't me.
No, I said,
But it wasn't BMW, it was just the guy that seen it. But they don't deal with motors that much.
Yeah, so they didn't know how to reverse motors and stuff like that. Well, there's 2 ways you can reverse a DC motor. You can change the field or the connection on the field, or you can change the connection on the armature. The industry standard is to change the armature because of all kinds of reasons. We'll look at that later. But they kept saying, okay, you can change the field, you can change, I said, no, yeah, you can change the field, but that's not the way you do it in the industry, because it can cost.
And they had a question on the test like that in Georgia.
That was my question though.
Oh, God.
Guys, pretty standard troubleshooting. Are y'all okay? Y'all understand that? By the way, 208, what category meter do we need? Gotta have at least Cat 3 meter. That's why we require it, because we're up on 208, right? Where would you start troubleshooting? Yeah, first thing, one of the first things, it's not the first thing you do. First thing you usually do, of course, in Richard's road is troubleshooting. What's my first road of troubleshooting? Now, what's my first? Know how the system operates. What it's supposed to do. What it's supposed to do. Second step, yeah, just look things over, right? Just look things over. You'd be surprised how many things I fixed. I just look things over. And then the third thing is when you start checking off power. Okay, so notice, here's the disconnect. They're doing the L1 side first, L1, L2, L3. And then they're doing T1, T2, T3. So on these contactors that's designed to run a three-phase, designed to run loads, the line side is going to be labeled L1, L2, L3. And then the output side is going to be labeled T1, T2, T3. Does that make sense? Everybody okay? And of course, the way we're supposed to mount these things, we're supposed to mount them vertical. Right? You understand? And where does power come in? Top. And the loads are connected on the bottom. And that's true on disconnects and all kinds of stuff. So I guess this is on this chapter, so y'all make sure y'all bring in y'all's, let's look at this real fast. Motor drives, DC motors, we're going to either drive them with what? Transistors or SCRs. Transistors we use for low power devices, low motors. And that's not true. A lot of times we'll hook these things in parallel. I've seen some DC drives where they'll have like 8 transistors connected in parallel, 8 transistors connected in parallel. That's pretty expensive. Normally on your big high power DC drives, you normally use what? You got these things called solar control with rectifiers. But what we're going back to is these are called, this is the symbol for what we call a bipolar junction transistor. And if we operate it, we got 3 regions we can operate this in. We can operate it as a switch, which means we either do cut it off or cut it on, all the way off. Or we can operate it in the active region. In the active region, it acts like a rheostat. So one region we operate it like a switch, the other region we operate it like a rheostat, electronically controlled.
You don't draw that with the circle on?
Why? Because it takes time to draw a circle. So do they do it? Is it, if I looked at the symbol in a symbol chart, you'll see it drawn both ways, with the circle or without it. Normally when I draw them, I don't draw them with a circle. The circles are hard to draw. But yeah, you'll leave them off. Normally we used to put solid state devices inside circles. Motor controls for solid state sensors are going to be inside a diamond state. But that doesn't, and that's usually always true. You see that?
There was one question we had on this, what changes the speed?
Not on this test. So an AC motor you can control it 2 different. You control DC motors. What we do to control the speed, we have 2 options. We can change the voltage on the field. And we'll look at this later. But it's kind of weird. If you lower the voltage on the field, the motor speed goes up. If you raise the motor on the voltage on the field, it slows down. The armature, which is the best way to do it, but screwing with the field can cause problems on shunt motors or compound motors. you lose the feel on the compound motor. If you lower the voltage, what does the motor speed do? If you lose any field voltage on a compound motor or a shunt motor, that sucker can run away on you if it's up and running. It could swing itself apart. So normally what we do is we control this guy right here. Because here if we raise the voltage, the motor speeds up. If we lower the voltage, the motor speeds slows down. Single phase AC motors, we don't want to change the voltage because the motor becomes extremely inefficient and the service factor goes to whack. So normally AC motors we control with a frequency. If we change the number of poles, if these are going to be set speed motors, right? You understand that? Everybody okay there? Or we change the frequency, but we can't change the frequency without changing the voltage. And we'll talk about that later. Yeah, if you just change the motor with frequency, you raise the frequency, the motor would stall. You lower the frequency, the motor would burn up. So you just can't play around with the frequency on an induction. So you have to vary the voltage. So if you raise the frequency, you have to raise the voltage by the same ratio. If you lower the frequency, you have to lower the voltage. Which is pretty important because when you program a variable frequency drive, that's what you have to tell it. You have to tell it what voltage the motor runs on and what frequency it runs on. And then it'll calculate that voltage to frequency ratio. It's really easy. Now, when we get into variable AC drives, this is where it gets very interesting. Huh? Losing means we lose current flow through the field. So this is why on shunt motors and stuff like that, we very seldom fool with the field, because if it's a shunt motor, if you lower the voltage on the field, if we're losing don't mean it's stripped out. If we lose the power going through the field. Well, if you lower the voltage on the field, the motor speeds up. So what would happen if you lost the connection to the field while the motor's running? It'll speed up and run away. Yeah, it'll run away. So that's why normally on these motors we don't fool with the field. We leave it, we don't. A lot of times out of U.S. Steel, the field was across the disconnect. It wasn't controlled by a relay. So they left the field voltage on it all the time. And they used to do that on purpose because the plant went down for a long time and they took the voltage off the motor would get moisture inside and it would rust. And if you ever seen the spacing between the rotor and the stator coils, they're just right there together. I mean, you can hardly put a cord in there. You get a little bit of rust on there, then your rotor would rust to the what? To the stator or those poles, and now you got a motor. So what they did out of U.S. Steel all the time, if they were going to be down for a while, they left power on all those DC motors. They left power on the field. So it wouldn't do what? So they'd stay warm all the time, and they wouldn't do what? They wouldn't condense and rust. Yeah, you get inside a motor that's been set up for a while. Guarantee you, they'll rust if you don't store them right. So that, understand, I didn't mean the field got lost. I mean we lost power. These are AT drives. By the way, they don't use bipolar transistors. They use these guys now. These guys are called insulated gate bipolar transistors, IGBTs. And what they do is they have a negative supply, they have a positive supply, a negative supply. Normally they use what they call pulse width modulation. It's really, really cool. But this allows them not only to do what? To change the voltage, it also allows them to do what? Change the frequency. This is the SCR drive using these guys here. Normally these would be the turn the motor on and turn the motor off. But this is the way we did it. And of course now, AC motors are dominating the motors. Used to it was DC motors. Why? Because we can control the speed. AC motors, the only way we can control the speed, we change the number of poles. I don't know what that means, right?
Yes, sir.
But now we using solid state devices, we can change. What advantage does an AC motor have over a DC motor? An induction AC motor. Oh yeah, AC induction are a lot cheaper per horsepower. So now, as far as electronic drives go, the predominant motors are Used to, the only advantage DC motors had over AC motors is we control, and it's still true. Alright guys, see y'all. Make sure y'all bring y'all's lab stuff in, right? I got everybody's fence back.
Yes. Hey, they say motors usually a lot better than they do now.
Yeah, they are because the roads have to.
Yeah, that's what I remember.
Yeah, they are.
I guess so.
Okay, I haven't seen you since, what they do. Go ahead, I know, go ahead. I don't see you that much.
Oh, you're in trouble.
That's good, that's good. That's
Yeah,
good.
You gotta go to principal's office. You are in trouble. I thought you left your phone at home.
I didn't know. You might.
I understand, but where's the budget that were due this morning?
They're over there now.
Yeah, I couldn't go do the budget hearing, because I didn't have your budget.
Well, the only thing that I was looking at was, I my mom.
Can you send them to me?
I can, but there's only one thing I had.
Well, that's all we'll have this year.
Plus the,
Everywhere. I have a
plus
job.
the software for the field. I actually have 20 on it.
$1,000 apiece for the AB?
Yeah, look.
No, it was $192 a piece,
Well, then I looked at it.
or 200, it's like $200 a license.
Well, good thing I didn't send it to you. And, of course I wrote it in.
And Catherine's chewing me out for not spending for not spending all the mechatronics money. We got